All right. So you remember, I don't know, maybe you missed that class. So we're just gonna do a quick test and I'm gonna show you guys something. Hey, you can probably see this right there. Okay, so here we are, and we're making 35 gauze. I'm gonna slide this plate of metal underneath, and we're making 56 gauze. So I thought I could get this, which is stainless steel. The stainless steel mesh, and I was hoping that it would be magnetic, and it is, but it's very, very weak. This is a really strong magnet, and so it's very, 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 very weak, which is awful because look at this. Yeah. I'm gonna break this. Not easy. So I'm not saying that this test is inconclusive because this is the wrong thing. Because I was hoping that put that behind and it would increase. So 33 and 33. So this is not doing nothing at all. Nothing at all. It's too bad. It's too bad. I just gotta find the right stainless steel product that...
Let me explain what Steve is saying here. There are several different types of stainless steels. The two main types are austenitic and ferritic, each of which exhibits a different atomic arrangement. Due to this difference, ferritic stainless steels are generally magnetic while austenitic stainless steels usually are not.
we can use. This is not it. This is definitely not it. Make a good screen for something. It's not for the project. I will carry a magnet with me when I go to the store and see if I can find some really good. Even if I found some steel one, it doesn't have to be stainless. It just might be hard to find straight steel. But anyway, no good. It's a flop. So we're gonna move on to part 2. And here's part 2 of this crazy experiment. Bought a roll of copper tape. So we're gonna do the same thing again. Coils roughly get 35 gauze. I'm gonna put that on top of it. Now let's see. 36 gauze, so nothing to brag about. It didn't do nothing. Take it off. 36 gauze, so another flop.
Let me quickly explain why copper did not work. Copper cannot be used as a magnetic shunt. Magnetic shunts are used to divert magnetic fields and provide a low resistance path for magnetic energy. Copper is a non-magnetic material, which makes it an ineffective material for magnetic shunting purposes.
This, on the other end, you can see a 58 gauze. So the tape is no good, so I have a roll of tape. If somebody wants it, let me know. I don't know what to do with it. And that. Now, the other thing that the only way that would even remotely work is if this thing was, it is conductive, which is good. Yep. So we have some buzz bar. That's amazing. Okay, well, 2 flops. I'm not gonna give up. We're not gonna give up. Okay, the screen, metal screen, just came in. This is really exciting. My lab is a mess, but I'm gonna clean up after this. So let's do the magnet test. Oh yeah, this is definitely very magnetic. Can't wait to see what it does. Woo! Hey, so I got this old power supply. It works, but the connection at the end has been used too many times and it finally died. It was a Genie rig. It's 19.5 volt. It's computer stuff, and I just took resistance of this. Now I forgot. So I got two coils in series, and I got them together in parallel. So I got 3.3 ohms resistance and 19.5 volts of power. That means about 6 amps, roughly. 6 amps pretty accurately. The idea is to make sure that we don't burn the ZK in the process. Now, I'm going to check the voltage on this. 19.7. That's good. I wonder, I think this is just a filler. Yeah, it's just a filler. There's nothing in the blue one. Okay. Disconnect U. We're going to power the ZK. So what you're witnessing right now, whoa, there was still charge on this. It's hard on the electronics. I should have touched them together before I did that. There's a small capacitor inside. Every time you touch a capacitor with a voltage, there's a spark that happens because it has to charge up. And everything resists change. Including electricity doesn't like to change. But anyway, I digress. I'm not here to learn physics. We're here to play. So, we got this. We're going to try that. So here's two coils in series. And then I got them in parallel. And we're going to plug that into the ZK screwdriver. This is really exciting. Like, stupidly exciting. I'm like freaking shaking in my pants right now. Pretty excited about this. Okay, I don't know if we're gonna do the test yet. Like this is really bothering me because I got the screen right here that we're gonna, let's turn this on. Okay, once again the ZK bomb proofing saved me. I wired it backwards. Knew the white one was positive, yet I put it on backwards. But the ZK is an amazing thing. Watch this. I'll probably burn it. There you go, it's on. Bomb proof. They designed the stuff for idiots like me. I just keep making stupid mistakes. Okay, 50%. Let's bring this down to 25%. I gotta put it. Okay, what's happening is there's more amperage needed. I said I need about 6 amps. Oh, this guy's only 2.3 amps. So all we're getting out of this is 2.3 amps, not 6. Yeah. Okay, so we're not going to make a lot of Gauss, but whatever. And doesn't like to go below 10. Let's see. Hold. 32, 44 Gauss right dead center. 43.7. See this one. 45. It all comes down to the meter catching it at the right time. 45. 45. Okay, so they're pretty much all even at 45 Gauss. Perfect. Let's disconnect this bad boy. Okay, how are we going to do this? How are we going to do this so we have somewhat of a good test?
Like a bird on a tree, I'm just sitting here. I got time, it's clear to see. From up here,
Okay.
the world seems small.
Well, the good news is there is an increase. You want to know the number, don't you? Yeah. Well, I'm going to keep it to myself until I take a bunch of reading. So we had, I said 45. Now we're at bouncing between 49.9 and 50.2. Whoops, I turned it off. Damn it. God, lights. Hold. 51.3. 51.9. Whoa. Oh, that's because I crossed the... Yeah, I went like this here, and then like, whoa, like 75. We want to make the reading all the same. 51.5. Okay, so we gain 5 Gauss per coil. The thing that'll be, whoa, 53. Oh, maybe because I did that. No, 49.9. So yeah, like right on the edge where the field is the strongest. I'm in the 70s, 75. Yeah, 70.5. So let's increase the duty cycle to 50%. It'll be easier for my meter to catch the high peak. Okay, right dead center, we got 60 Gauss. Remember guys, increasing the duty cycle does not make the field stronger.
Steve, let me point out something. In general, increasing the duty cycle of a PWM signal will result in an increase in average current, which can lead to an increase in magnetic field strength. It's important to keep in mind that the relationship between the duty cycle, current, voltage, and magnetic field strength is a complex one. But for our purpose, and for the sake of keeping things simple, I will agree with your statement.
It just makes it easier for my meter to catch it. 61.3, that's why I always do it at 1 hertz and 50% duty cycle to allow time for the processor in there to read it, right? Because it goes too fast if not, and the processor can't catch it. So increasing it to 50% does not make the field stronger. Wow, yes, in physics term it would, but not for application, not for per se. And just makes it easier. The biggest draw here, the biggest gain we get is the meter can read it. There is an increase, but it's nothing. So 61.6. 64, 62. Okay, so leaving this at 50% duty cycle, we're gonna put, so we've established already that they're pretty. Just a quick bracket. You can see I'm getting different reading all over the place depending on where I put my Gauss meter, depending on the duty cycle. That's due to the limitation of my cheap Gauss meter. One day we'll have a $2,000, a $3,000, a $4,000, $5,000 Gauss meter here, and we can take some actual reading. We can also verify some of the claims some of the companies are making, and then we'll see where we're at. We might find out that our 50 Gauss unit is actually 10 times more powerful than some of the big names out there that claim to have much larger number than us. Time will tell. Pretty much all the same, right? So we're just gonna see. So 10 hertz, 50% duty cycle. Let's come up here and do this, right dead center. So this coil makes 58, 59, 60, 62. Okay. The other thing is, I don't know if having a big screen like this makes a difference or not. I don't know. Let's see where we get now. Yeah, like right now I'm at 80, 81, 82. Yeah, 82 Gauss with this big plate. 82.7 with this plate. 83. So let's put the plate under this one. Hold. 81.7. Remember, my meter is only accurate to 2% or something like that. 83, 82.9. Okay, from 60. So from 60 to 83, and on the grill, from 60, 83, 64. So I'm going to go ahead and say that the grill is a flop. Let's make ourselves, you're probably wondering what I'm doing with tin snip in here, eh? Let's make ourselves a square. To the same level as the magical. I got a couple things I want to try with this. We're gonna have fun here. Oops, on this. Okay, hold. So right now I'm doing 60, 60.3. Hold, dead center. We're doing 55. So we go from 55 to 60, so we gain 5 Gauss. Now what happens if I increase the density of this? And I put that in there. Put this in here. Read the same place. 67. 68. Okay. I'm gonna do something. Where did I put my tin snip? We gonna. The funniest thing is, when I bought this on Amazon, I was looking at the review, and would you believe it? Somebody complained that the wire mesh was not straight, and when they're cutting, they were following the line, and they're all mad that they end up cutting it crooked, and they wasted a ton. It's like, you're gonna be kidding me. People are weird. That's all there is to it. Okay, now here's folded 4 times. Okay. Okay, so our master here, which is the goal for us to get at. Okay, right now I'm getting 80.3. Okay, this one 54. This one, this time around I'm getting 67. And this one 75.7. 74.3. Oh, it's bouncing. Let's put it down. 74.5. Okay. Going back here to our big guy, 78. All right. So, oh, they're getting warm, these bad boys. How you sit moving. Okay. So, this is pretty light to put behind. It'll just be a matter of making sure that it's freaking really down flat. So, okay, put it like this. Hold. Wow, 78.9. Like pushing. Oh, if I push really hard on it, I got 81. So just be. I could have to mash it with a hammer. 79.1. I got the 81s. Okay. What about this guy? That's the 263. Now, I'm wondering if, because this has a bigger surface area, right? Are we going to gain even more if there's more metal? Going like this. 81.7. Do it again. 79.7. Do it again. 80.3. Okay, so we're not really gaining much of any. Should be able to cut this guy in half. I knew sooner or later I was going to find something that works for our purpose. What the hell? It's like I'm freaking sewing something or basket weaving. Okay, put it there, turn it off, turn it back on. Hold 75. Go to this one. Off, on. 75.6. Okay, so having a bigger one allows to catch more that goes outside. Maybe not. 76.3. I did 76.3, now I did 75.9, right?
Quick word, Steve. As your coil's heat goes up, so does the resistance. This relationship can be described by the temperature coefficient of resistance. This increase in resistance causes more heat to be generated, which in turn leads to an even greater increase in resistance, creating a positive feedback loop. In turn, higher resistance with same voltage applied means less amperage and in turn less Gauss. This could be why you are seeing lesser Gauss output right now. To avoid self-heating and to prevent damage to the wire, or fire, it is important to design electrical circuits with adequate cooling and to limit the current that flows through the wire.
Okay, so I got this folded in 4. Let's try 8. Let's see what happened with 8. Hold. 80. Off, on. Oops. hold 82.2. Okay, so I'm going to try to keep it like this. So from 54 to 80.2 to 75.3 to 84. So that's really light. I mean, oh yeah, it's half the weight of this, right? It's pretty good. And I think just one of them gives us a pretty good thing. So I still think this is not a flop. This is good. Folded in 4 like this, I think is excellent. So from 55 to 75. We're basically going from 55 to 75 just by adding this, which is good. I like it. Turn this off. Turn this off. Okay. For this test, I have my 24 volt power supply. I have 1 hertz 50% duty cycle. Okay, and it's just a temporary. I'm building this PEMF. There's a mat with our typical 10 coils on it. They're on the other side, obviously. Okay, now I have this center holding the probe this way. The idea is I'm going to slide different thickness of screen, and then we're going to see what we get out of the Gauss meter. So this is going to be interesting. All right, here we go. I'm going to turn it on. There, it's on. And we're rating 22 Gauss. We're going to start with a double sheet. I'm going to put that underneath, not changing anything. And we went from 22 to 28. Just trying to make it. Yeah, there you go. It's on it. Yeah, we're at almost 29. All right. We're going to try this one has 4. Now we went from 22 to 31. Excellent. This one has 4. If I grab one of them plate and put it underneath, we're getting 31. So we are getting more with just 4 of them things. And as you can see, it's kind of...
So I hope that answers a lot of you guys' question. It was a long video, but I wanted to keep a lot of footage in it to show you guys like all the work that goes into that and all the testing. So I finished that mat. I put 4 layers of that mesh. It's just steel mesh, chicken wire, 1/8 of an inch gap in between. Got it on Amazon. Probably cheaper to find it at a local hardware store. But anyway, it was a really good test. I'm really happy about it. It's easy to work with. It's light. It's cheap. And then we have a 40 to 50% increase. So we can't ask for much better than that. So you guys stay safe, and we'll see you soon on the next video. And Patreon is in the link. They're the one that's gonna get all the information first. And the bipolar stuff is happening. It's made. I actually been using it for a few weeks now. I don't know when this video is coming out, but as filming this video, I've been using the PEMF for quite a while, and amazing stuff. Okay, stay tuned. Talk to you soon. Bye.